So in this session, we will introduce the CFD basics and the use of the software ANSYS Fluent in engineering application. To start with, we know that fluid dynamics is a very important science that is present in a lot of engineering application. This is why fluid dynamics is very interesting and challenging field to study and to conduct research on. In real world, almost everywhere fluid is present. So if we take, for example, a design of airplanes or design of cars, so when you want to design a car, you need to know how, let's say, when this car move, what are the forces acting on it from the air. You need to study drag forces. You need to study lift forces, which will involve fluid dynamics. You need to study also what is the pressure distribution around your car to decide on the type of materials that should be used for the body of your car. So this is one application involving fluids. You have also, whenever you have piping systems, you have a flow that is circulating in the system. You need to understand the characteristic of the flow, how the pressure is varying, to select the appropriate pump to use in your system, for example. Another application, even in heat transfer applications, if you have a heat exchanger, you have flows of fluid circulating in the heat exchanger. So you need to know how the Reynolds number will affect the performance of heat transfer, which will relate then two sciences, heat transfer and fluid dynamics. In design of HVAC systems also, of course, fluid dynamics is of high importance. So you have a, let's say, an inlet, an outlet, and you need to understand when you supply air, how it will circulate in your space. And this will be affected by fluid dynamics. So fluid dynamics is nearly present in the majority of engineering applications. And this is why we need to understand the dynamics, the physics behind fluid dynamics in order to be able to come up with models describing fluid motion. So in brief, any fluid flow can be solved or described by three basic physical laws or by three equations. So whenever we have to solve a problem, we start to write equations. The first equations that can come to mind is conservation of mass. So in a certain system, I should do a balance of fluxes to decide to come up with a relation between inlet fluxes and outlet fluxes. This is the continuity equation. A second equation will be the momentum equation, which is known also as Navier-Stokes equation. If you remember in fluid mechanics, for the particular case when you have constant density and viscosity, you will have then to deal with Navier-Stokes equation. Now, these Navier-Stokes equations were very challenging to solve. They only present analytical solution in very specific cases. So in fluid mechanics course, you have learned in case of laminar flow, how to find the solution of these equations. And you come up, let's say, with a parabolic profile of velocity, which will give you zero velocity near the boundaries and maximum velocity at the center. Okay. You have learned also how to determine, let's say, flow in between concentric cylinders. So this application is also widely used. So how we establish the profile of velocity in concentric cylinders, how to find flow variation between two parallel plates. So if I have one fixed plate and the other is moving, then I can obtain a linear profile of velocity. So these are simplified solutions for very simplified problems. But in real life, you will encounter much more complex scenarios. First, you might have turbulent flows. So whenever I go from laminar to turbulent, the solution of Navier-Stokes equation becomes much more challenging and will require additional equation to write to solve for the turbulence variables. And even sometimes for some type of laminar flows, if the geometry is very complex, this will require numerical simulation because you don't have a closed form analytical solution. Now, the second type of equations that is widely used, as we said, is which to obtain Navier-Stokes equation is the momentum equation. And these equations consist on just writing Newton law on your element. So sum of forces equals ma. And from here, we derive Navier-Stokes relations. I will remind you of the method to derive these in coming slides. And the third equation is the energy equation. So you do a balance of energy. You consider all possible heat fluxes, conduction, convection, radiation, and then you put them in one equation to relate, let's say, temperature to other variables in your domain. So now, to remember a little bit how we come up with these equations, we can work in general with two approaches. We can work on the micro scale, we can work on the macro scale. Okay, when you want to solve for a velocity field, a temperature field in a space, you need to know at each point what is the temperature. So you need to go to micro analysis. Okay, while for example in some fluid problems you have, let's say, a big control volume, you have a reservoir of water, for example, and you are supplying water from this level, and you have a small outlet here, for example, let's say. So no need, if you want to know how the level of water in your reservoir is varying with time, no need to do a micro scale analysis. You will consider your control volume as the whole reservoir, and you will say, to know how the height of water is varying in this reservoir, I should do a balance between inlets, outlet, and storage. So you can just say that storage term or variation of mass in my reservoir, dm by dt, okay, is equal to what is coming, the flux coming in, so m dot n minus m dot out. And then if I give you the flow rate, so for example, if I tell you that you have 2 kilograms per second coming in and 1 kilogram per second getting out, then you can say that the variation of mass with time is equal to 2 minus 1 is equal to 1 kilogram per second. So the mass of water in this reservoir is increasing at a rate of 1 kilogram per second. And then this can help me to find the height variation. How? You know that mass is density times volume. And volume, the volume of water in my reservoir is the cross-sectional area times the height. So V will be function of time because the height is changing with time since the mass is changing with time. So I can replace M by rho times cross-sectional area, which is constant, times HT. So this is M. So now if I derive M with respect to time, and I know that the density and area are constant, so I can take them outside of the integration, then I can find that h of t, the derivative of h with respect to time, is a constant, okay? And this constant is equal to 1 over the density of water times the cross-sectional area of my reservoir. So you'll obtain a constant. This means that h will vary in a linear way. So h will increase linearly with time. Okay, so here you didn't need to do a micro analysis. On the other hand, if I give you the problem, you have a room and you introduce air in it and you have an outlet and you want to know how the air will be distributed in the space, what will be the temperature at each location, what will be the velocity at each location, okay? Then you need to do a microanalysis. First, you need to divide your space into very small parts. So this is the meshing part. So you mesh your space, you divide it into small elements, and for each small element, you will write the balance equations. You will write the continuity equation, the momentum equation, the energy equation, and you should solve for these equations for the whole domain in order to be able to solve for temperature field, velocity field, concentration field, etc. Okay? And of course, to be able to solve for this, you need to know your boundary conditions. So what is the temperature at the inlet? What is the velocity at the inlet? And what is the type of condition I can impose at the outlet? So you can solve for the variation of temperature, velocity, and concentration within your space. So since I need to use my balances on on the micro scale, I need first to develop general equations for a micro element. So I will take a very infinitesimal control volume. So I will say in any space, if I'm working in Cartesian coordinates, X, Y, and Z, if I consider a small element and I want to apply on it conservation of mass, what should I do? I should consider that I might have a transient application. If I have a transient application, I might have accumulation of mass within the control volume, like I had in the case of the reservoir. If the total inlet rate is larger than the outlet mass flow rate, I will have accumulation of mass in my control volume. If they are equal, if m dot n equals m dot out, then I have, if you want, no accumulation, the mass and the control volume of the fluid will remain constant, and I will just have that what is coming in should go out. So this is a steady case. And I can have, on the other hand, reduction of mass within the control volume if m dot out is larger than m dot in. So to take into possibility all possible scenarios, I will write the general equation. The general equation for any small control volume is the accumulation of mass within this control volume, which is represented by del t, which is the partial derivative with respect to time of the mass of fluid within the control volume. Now here, if I'm performing control volume analysis, no need to perform integration, and already I'm taking a very small volume. Okay, so I can say that I am working on an elementary mass dm, and this mass, this small mass, is just rho times elementary volume dv. And here, for example, if I consider the following element, if it's a cubical element, I can say that I select, let's say, dx, dy, dz equal to a very small number tending to 0. And I say that the elementary volume dv is dx times dy times dz. Okay. Now, so this will represent the transient term in my equation, transient storage term. And this term will be 0 if I have a steady application, then it will drop out. Okay. Now, I should add everything, every mass flow rate getting out, and I should subtract every mass flow rate going in. This will give me 0. Okay. So in this case, this is the balance. If you take these mass flow rates to the other side, you obtain what is the result. We know that the accumulation of mass is sum m dot n minus sum of m dot out. So now I should consider all possible fluxes of mass on my element. To do this, I illustrate these fluxes. I consider that since I have 6 faces, Okay, I might have let's say if I have flow in different directions. So let's say you have a flow moving in x, y, and z. Okay, so if I have this in this direction, which is perpendicular to the face, okay, I have a mass flow rate coming in. To calculate this mass flow rate coming into this face, I should do, you know that the expression of a mass flow rate m dot is rho times A times V. Okay, you have rho is the density, A is the cross-sectional area, and V is the velocity perpendicular to the face. So if I consider this face, what is the area of this face? Since this face has a certain thickness along y, which is dy, and a certain thickness along along z, this is z direction, so this is dz. So the elementary area of this face will be dy times dz. So I can, since I'm considering elementary mass flow rate on this small face, it's rho a dv, rho v dA, and the elementary area is dy times dz. So for this mass flow rate, I have to multiply the density by the velocity perpendicular to this face. Since this face is in plane yz, so the velocity perpendicular to it will be along x. So I should multiply by the component of the velocity field along x. In general, the notation way is the following one. If I'm working in frame x, y, z, I consider that the velocity field has a direction component along x that is named u, a component along y named v, small v, and along z it is small w. So I have here, since I'm considering the face that is yz, then the flow crossing it will be along x. So I will multiply by the component of velocity along x, which is u, and dA is dy dz. Okay. So this is how I find the expression of the first mass flow rate, this one, rho u times dy dz. Now, this flow will cross the control volume and will get out at this stage here. Now, how to relate the mass flow rate at the inlet and the mass flow rate at the outlet along x direction? We consider that because the velocity u is changing with space, okay, the mass flow rate at this face can be different from the mass flow rate at this face, and it will be affected by the value of u. So u will vary. Since here we are changing x position, we need to determine how u is varying with x. And we know that if we know u function of x, okay, if I take a position x and another position that is very close to it, and here, what is the distance between these two faces? The distance between these two faces is dx. So we have here at this face, you have u of x, and for the other one, you have u at x plus dx. Okay, so you have an inlet here and an outlet here. And how can I relate the velocity crossing this face to the velocity exiting this one? We have what we call Taylor expansion. You have a relation. If I have a certain function, Taylor expansion will allow me to relate as values of this function at two close positions. And the rule is that u at x plus dx is equal to u at x plus the partial derivative, okay, of the function u with respect to x, and also dx, and also this will continue for, you have other terms related to the second derivative, third derivative, etc. So this is a Taylor series expansion, we call it. In general, the other terms will be much smaller than the first two terms. This is why we say we can limit ourselves to the first two terms and will obtain a small error. This is called the truncation error, because we are neglecting some terms compared to these terms. Okay, so here we'll limit ourselves to the two first terms, which is u and the first derivative of u with respect to x times dx. Now, when we do this, okay, we can relate the value of the function at x plus dx to its value at x. So for example here, okay, you have rho u times dy dz. The function of interest here is rho times u, because sometimes if you deal with incompressible fluids, not only the velocity is changing with space, but also the density. So if you deal with compressible fluids, then you should take into consideration also variation of density with space. And if you deal with incompressible fluid, then your function will only be u. Here, since we are developing a general equation, we will consider that the product rho u can vary with space. So if I know that at position x, the value of the function is rho times u, I can say that the value of this function at x plus dx is equal to rho u plus del rho u by del x dx. And then I multiply this result, which is the value of rho u at position x plus dx, okay, by the elementary area. So this is at x plus dx. I multiply by the elementary area, which is dy dz. Okay, in this way, I have obtained an expression for mass flow rate crossing YZ in and out. Okay, now I will do the same procedure for all other phases. Okay, so for other phases, you have for this phase here, what will change is that now the velocity crossing this phase is perpendicular to plane xz. Okay, so it will be along y. This is why here I consider, instead of rho u function, I consider rho v function. Okay, and since I know rho v at section at a certain level y, okay, if I want to find its expression at y plus dy, I can use the Taylor series expansion, and then I get rho v plus del rho v by del y dy times the elementary area, which is dx times dz. And I do the same work for the third direction, which is along z. So I have these fluxes. And now what is different is that the velocity will be along z. So the function is rho w. Okay. When I express all of these, yes.
في جو عوايدة منه مبين السكرين عنده.
But the remaining one are seeing the screen.
دكتور هو قايل انه فينا نعمل
السكرين من تحت للبرزنتيشن.
you want to put it on the whole يلا بقدر كبرها بس انتوا قاشعين السكرين بس شخص واحد مش قاشع على السكرين.
لا اشعه على السكرين بس بدي اياك تكبريها للبرزنتيشن.
اوكي
ميرسي
فاين.
كثير. ميرسي
هيك منيح.
ميرسي دكتور.
Okay. So now, after we determine the expression of all mass flow rates, we get 3 mass flow rate at inlet, 3 mass flow rates at outlet. Now we are ready to plug into the balance. Okay. So what we will do then, we will say that the storage term here, what is the storage term? It's del by del T of rho times dV. And as we said, dV for this element is dx times dy times dz. Okay. Plus you have for I will take the first inlet. If you want now, I will start with summing outlet, because the mass balance equation is the storage term plus sum of m dot out minus sum of m dot in equals to 0. So now I will consider all outlet flow rates. The first one is this one. So I do rho u plus del rho u by del x dx times dy dz. The second outlet is the green one. So it's, sorry, the upper one, which is rho v plus rho del rho v by del y dy dx by dz. And this is my third outlet here. The third outlet expression is rho w plus del rho w by del z dz times dx dz. Now, once I'm done with sum of m dot out, I move to determination of sum of m dot in. So now I should subtract all inlet fluxes. So I should do minus rho u dy by dz minus rho v dx by dz and minus rho w dx dy. This one. Okay. Now it seems that it's very complex relations, but you will see that I can do a lot of simplifications now. So if I look at my equation first, all terms share the dx dy dz element. So I can simplify dx dy dz from all terms. So this is the first simplification I can do. Just 1 second here. You have to first let us remove the x dy. هنشوف انه dz كمان will be removed at the end. Okay, because look, before removing the x dy dz, okay, before removing this, you can do a simplification which is the following. هنا عندكم plus rho u dy dz. لو هنا عندكم minus rho u dy dz will cancel out. يعني هيدا الترم اصلا حيروح. وعندنا هون plus rho v dx dz minus rho v dx dz, it will cancel out. So you can drop this term, and you have rho w dx dy and minus rho w dx dy, which will cancel out. Now for the remaining terms in your equation.
دكتور
نعم.
دكتور
نعم.
سوري رحت من عند الارسال. شو كنا عم نعمل simplification؟ كنا عم نمشي على اساس دي اكس دي واي دي زاد وراح.
Yeah, I will repeat. Okay, after you write the balance, okay, after you write the balance, you will start to simplify terms. You have a lot of terms that will cancel out, because for example here this term is rho u times dy dz. Okay, from this side here you have minus rho u dy dz, so this term will cancel out. Okay, same for this one, you have plus rho v dx dz, and here minus rho v dx dz, so this term also will cancel out. And from this side you have plus rho w dx dz minus rho w dx dz, it will cancel out. Now if you look at the remaining terms, all remaining terms are multiplied by dx times dy times dz. So you can simplify dx times dy times dz, dx times dy times dz, also here simplified, and then you will obtain a much simpler relation. The relation will be the following: del rho by del T, which represent the variation of density of the fluid with respect to time, okay, plus del rho u by del x plus del rho u by del x plus del rho v by del y plus del rho w by del z equals to 0. This is the continuity equation on the micro scale. Okay, now you have several specific cases. If you deal with incompressible fluid, so if your fluid is incompressible, then rho will be constant, so this term will cancel out, and you can take rho outside of your derivatives for all terms, and it will cancel out. So if the flow is incompressible, this equation will reduce to del u by del x plus del v by del y plus del w by del z. This is the continuity equation for an incompressible fluid. Okay. Now also we can demonstrate that this is the continuity equation so this will work for any incompressible fluid. So this is for incompressible fluid. Now, if you have a steady application, okay, in case you have steady application, but you don't know if the fluid is compressible or not, in case it's steady, so del rho by del T also will cancel out, but you will not be able to remove rho from the derivative with respect to space. So if steady, the relation will be, so let me add here, if it's steady but not incompressible, so if just you know that it's steady application, then the equation will be del rho u by del x plus del rho v by del y plus del rho w by del z. Okay. Any question on how we derived the continuity equation?
دكتور أنا بسألك عن سؤال، هي إذا steady معناتها it doesn't يعني مش هتغير مع التايم.
steady يعني no change with time. بس يقولوا لك steady this term will drop.
اوكي بس بهالحالة
بس مش يعني incompressible، يعني الرو فيها تكون variable with position.
اوكي هلا عرفت الفرق.
اوكي.
Thank you.
Welcome. Okay, 1 second. Okay. Now, if we want to derive the momentum equation, we'll follow a similar procedure, but instead of taking here fluxes of the different fluxes, inlet and outlet fluxes, we will consider the balance of forces on the element. Okay, we'll go more into detail when we do a review of conservation equations, but here just to summarize the procedure. When I want to get the momentum equation, I base myself on Newton law. So I write sum of forces equal ma on this element. And when I do this, I should consider all external forces acting on my element. And to have a general case, I should consider all possible types of forces. Yani, body forces, surface forces, pressure forces. Sometimes if I have, I can include electrostatic, magnetic forces, etc. So you will see that in ANSYS Fluent, when you want to implement forces, you have all options. you have the option of implementing electrostatic, magnetic, body forces, etc. Okay. Now, for this analysis, when we develop Navier-Stokes equation, we consider that the dominant forces are body forces like weight. We have pressure forces. Okay, so you should consider the pressure field to be able to find pressure at each face. And for example, if I consider this face, the force on it is, the pressure force on it is P at X, okay, times dy dz, okay, while for the other face, okay, this one, you do also same concept. You use Taylor expansion. If I know the pressure at position X, the pressure at X plus dx will be P at X plus del P by del X dx.